Okay, any question from this time? So yeah, let's have a small review from this time. So this time we start talking about this quantum mechanics of a composite system. And well, composite system is just I would like to think it is several quantum systems that are interacting with each other. And so I kind of look at this. So you have several systems, and individually they have those Hilbert space H1, H2, H3, etc. And then together the space of every system interacting with each other will be this H1, tensor H2, tensor H3, etc. And then we have this postulate 4 says about what are the Hilbert space, what are the state, and what if you do a unitary on one of the system, and what if you do a measurement on one of the system. And we have this notation. So you have two systems, and the state will be if the state is not entangled, we can have this form psi tensor phi, and then we have a whole bunch of abbreviations. So the most simplest way to write this is just a psi phi. And also sometimes we'll abbreviate for the unitary or operators on each system also. So you should write a tensor b as 4, but sometimes people also write a b. Okay. And yeah, we say for composite system there is entanglement. Okay. So entanglement means that because this state H1 tensor H2 is really large, it's more than what state. This is more than just stay in H1 times stay in H2. Okay. For example, you can have this entangled state is this 1 0 plus 0 1 or divided by square root 2, and I think you should have done in your homework. You can show that this thing cannot be written as some K8 tensor KB. Okay. So this kind of state is called entangled state. And we go through this example that we don't go into detail, but with the composite system, you can prove that generalized measurement can be done by just doing a computational basis measurement preceded by a unitary evolution. So if you do some unitary evolution U that depend on your measurement, and then you have a HRA system, this ancilla system, and then you just do computational basis measurement on this ancilla system. Then you see the end result on your original system Q will be just doing your measurement, your generalized measurement with measurement operators big M sub small m. Okay. And we kind of give a proof. It's not quite complete, but we argue that you can actually find a U that has a desired property where you have a U on side, you will apply this M sub M on your original system Q and turn your other system into this computational basis M, and then you sum over different M. And yeah, then you do a whole bunch of calculations, things like this works out. Okay. And yeah, so this is the example of our composite system. So you do a generalized measurement on system Q, then it's you can do it with computational basis measurement with the following steps. So you get a HRA and CLR system, and you do this U that depend on M, and this is entangled unitary, so it does both. I guess the correct way to say this is entangling unitary. So entangling unitary apply on both U and both Q and M, and they measure M in computational basis. Then you will get the outcome in M, and but they only want to see what happened on Q, so you just throw away register M. Okay. And I guess this here we have a bit of a weird part about throwing away, and we'll get this a bit more formal later on. But yeah, not really. But I guess we'll have in the next chapter we'll talk more about what happens when you throw away a register. Okay? So that's a bit of a spoiler for next chapter. So any questions so far? This is what we have done in this class. We do this composite system, and we talk about this composite system, and we say generalized measurement can be is equivalent to computational basis measurement on a composite system. But if you just do this unitary U, that correspond to your measurement M. Okay. If not, then let's go back to entanglement. Okay, so let's talk a little more about entanglement, and let's see some application of entanglement. So we have two applications. First is superdense coding. Okay, and in this application, I guess, well, what we want to do is very straightforward. So in this application, we have two pairs. So Alice and Bob, just like before in QKD. And here they want to do something very straightforward. They want to send the classical information from Alice or Bob. So Alice just want to send some string to Bob. Okay, so there is A and B, and yeah, there are some 0, 1, 0, 1, 1, 0, etc. that Alice want to send to Bob. Okay, so it's quite straightforward, and so. Well, then if there's a classical channel between them, Alice can send them to Bob. Okay? But what we want to do here is we want to Alice want to send this classical string to Bob, but instead of sending just a classical bit, he want to send she want to send the quantum states. Okay, so she want to send some quantum state, and the idea is that she wants to send a quantum state instead of classical bits, and they want to have the number of qubits sent to be smaller than the number of bits sent here. Okay? So they want to use the fact that the quantum state can be is more general than classical bit, and to send more classical bits in these quantum bits. Okay? So that's the idea. And indeed, they can do this, but with a bit of weird setup. Okay, so superdense coding on the very high level is that they can send 2 classical bits by sending only 1 qubit. Okay. So you see that sending qubit is more efficient than sending classical bit. Okay, and this is called superdense coding. But there is, as we'll see, there is a few trick part. Okay. And the trick part is entanglement. Okay? So you can actually prove that. So if this is just a one-time thing, and say you have n bit, so say they want to send some n bit x. Yeah, so that's a bit of a derailing. So they want to send some n bit string x, and with just m qubit phi. And if they just do this, then n need to be about equal to n for this encoding decoding to be successful. Okay. But they can do a bit of pre-sharing thing in this by using entanglement. Okay, so so this is I guess the trick part of superdense coding is that Alice and Bob can initially share a whole bunch of entanglement. Okay, so we'll see that. So this shared entanglement, we can think about this as some kind of resource, and they can be very useful to do a whole bunch of tasks. Okay? And superdense coding is the first application. So we have Alice and Bob, and before they want to send a message, so maybe in their downtime, they just started to share entanglement between them. And by sharing entanglement, so usually people draw entanglement kind of like this. So Alice hold 1 qubit. So what is this entanglement to be shared is 2 qubit state. Okay. So the shared entanglement is Alice is holding 1 qubit and Bob is holding 1 qubit. And those 2 qubits, we think of them as a composite system, and those 2 qubits can be in an entangled state. And usually people just do this entangled state. Okay. So this is psi equal to 0, 0 plus 1, 1 over square root state. And this state has many names, and I guess we didn't have it here. Sorry. Yeah. We'll probably talk about this later. Yeah, this state has many names, and but for now, this is the shared entangled state. Okay. And yeah, as we said, Alice has 1 qubit of this state, and Bob has another qubit of state. And it's an entangled state, so you cannot really say what's Alice's 1 qubit and Bob's 1 qubit, because to describe the state totally, you need to say these 2 states is in this 0, 0 plus 1, 1. So this qubit is neither in 0, 1, 0 or 1, and this is neither in 0 or 1. Okay. Yeah. And yeah, as we said, the important thing here is psi is a fixed state. So this pre-shared entanglement doesn't depend on what Alice want to send in Bob to Bob. So they can just do this when they have free time and try to share those entangled states between Alice and Bob. And I guess one way to do this is they can do one quantum communication. So Alice can create this state on her own side. So you just create a whole bunch of pair of qubits that are in 0, 0 plus 1, 1 state, and just send the second qubit to Bob. Okay. And when they have a message, when Alice actually have the message, this X, she wants to send to Bob, then they can start doing the superdense coding. Okay. That's the setup. You need this resource, that's entanglement between Alice and Bob. And this entanglement is going to be used when I do superdense coding. Okay. And okay, so this is the setup of superdense coding. Alice and Bob share a whole bunch of entangled pair. And actually, if they only want to send 2 bits of they only want to send 2 bits of classical information, then they only need to share 1 pair of entanglement. Okay. And yeah, so let's see how it do. So yeah, so now with this pre-shared entanglement, Alice can send 2 classical bits by send 2 classical bits of information by sending 1 qubit. So this is what Alice do. And what Alice do is well, there are 2 classical bits she want to send, so it can be 0, 0, 0, 1, 1, 0, or 1, 1. Okay. And what she do is she just do something on this pre-shared pair. Okay. So remember, Alice and Bob share a pair entanglement. Okay. Alice B and okay, so they share this thing, and Alice will do something here. Okay. And so there are 4 possible messages to send, and there are 4 possible things that Alice will do. So if the message is 0, 0, then Alice just do nothing. And the message is 0, 1, and then she will apply a Z gate on this qubit. If message is 1, 0, she will apply X gate. And if message is 1, 1, then she will apply, I think this is X gate, then Z gate. But it doesn't really matter if she applies Z gate, then X gate, then they get a global phase here. So they just get a -1 extra global phase. Okay, and but anyway, this is a protocol, and let's see what happened after the first step of protocol. And so we want to see what are state between these 2 qubits. So there's 1 qubit here and 1 qubit here, and let's start with 0, 0 plus 1, 1, and let's just see what happens when you apply some gate on the first qubit. Okay, so with 1, 0 gate, so let's have an example here. Message being 1, 0, Alice want to apply a Z gate here. Okay. And so we want to see what happens. You apply Z gate on the first qubit of this 2 qubit state. Okay, and then we can go back to our postulate. I think here. So this is what this happens. So z get on first qubit actually means we apply z tensor identity on the 2 qubits. Okay, and let's go back. Okay, so we do z tensor identity on the 2 qubit, and so what happened is that yeah. And so you have a z tensor identity on this thing, and then we go by linearity. Then it's a z tensor identity on 0, 0, and because each slot should just do multiplication itself, so it's a z on 0 tensor identity on 0. Okay, that's the idea. So we have yeah, we have it here. So we have a z tensor identity is the gate we apply is z on A and identity on B. Okay. And so we want the z tensor identity on 0, 0, 0 tensor 0, and 1 tensor 1. And we have a distributed rule, so we can calculate this on this and this on this. And the z tensor identity on 0, 0 is z on 0 tensor identity on 0. And similarly, the second part, we have z on 1 tensor identity on 1. Okay, and now we can resolve this back to simpler notation. So z on 0, 0 is eigenstate of z, and so it's still 0. And identity on 0, well, doesn't do anything. And then the second part, well, this is still eigenstate, but 1 is the minus 1 eigenstate of z. So we pick up h1 minus 1 phase here, and then we tensor. Yeah, so we have a h1 minus sign here, and I guess I'm missing. This should be missing parentheses here. So it's 1 ket and parentheses 0 minus. And anyway, so on the second term we pick up the h1 minus sign. So in the end, we get this 0, 0 minus 1, 1, and with the 1 square root to us normalization. Okay, so that's an example calculation, and then we can, so similarly we can see what's happening. Hopefully, I guess I'll stop here for now. So anyone has a question on this calculation? This is more complicated. Let's just stare at this for maybe 1 minute. Okay with this calculation? 你说这个部分吗？这个是因为一是 z 的负一eigenstate嘛，就是 z 是这个东西，然后我写在旁边好了，就是 z， 然后抱歉写错了 ，z 然后一的 state 等于负的一这样子，就是多一个符号出来，然后我们括弧起来 ，OK。With this, so I guess this is the basic of all these composite system calculation we want to do. Okay, so important to be sure that we are okay with this first example. This is the first example of we actually do composite system calculation. Okay. If this is okay, then we can. Okay, then let's try to go very fast about the other things. Okay, so then the other thing, the next thing we do is we do 1, 0, and we apply x on the first qubit. And hopefully from this example, you see that what we do is we just never change the second qubit because we have identity on second qubit. And so what we do is we apply x on 0 to 1. And x gate being switching between 0 and 1, x gate will just make the 0 ket into 1 ket and 1 ket into 0 ket. So you get this result. Okay. So you become 1, 0 plus 0, 1. Okay. So I guess I can write the x gate here also. X gate equal to 0, 1, 1, 0, and so if you apply where am I? Here. Okay. X gate equal to this thing. So if you apply X gate on the 0 gate, which is equal to the 1, 0 vector, you get this 1 here, so you become the 0, 1 vector. And similarly, you have a 0, 1 vector multiplied by X gate, you become the 1, 0 vector. And that's from ket 1 to ket 0. Okay. So X will do this. And yeah, finally, if you have the 1, 1, you have 1, 1 as message, you apply IY, which is you just apply X, then apply Z. And hopefully we get the minus sign correct. Okay, so minus sign correct. So apply X, you become this thing, then you apply Z gate. And Z gate will say if you have a 1 on first qubit, you get a minus sign. So you see you have a 1 on first qubit, you get a minus sign here. So 1, 1 is you apply X gate, you apply Z gate. Okay. And yeah, now we have a name for this state. Okay, so I say there is a name for this state, and here are the names. Okay, so those 4 states are very famous. They are called Bell bases. Okay, so this is a bit of simple spoiler. So those 4 states actually become bases in 2-dimensional space, in this 2-qubit space, and so it's called Bell bases or Bell states or EPR pairs. And okay, so this name EPR pair is a bit more confusing. Sometimes people mean, when I say EPR pair, they mean okay, they are very different notation. Okay, EPR pairs can be either the 4 states, but sometimes when I say EPR pair, that means this state is a 0 state in particular, or sometimes they mean this. I think they mean this 1, 1 state in particular. So EPR actually has it actually has a historical. This name EPR pair has a historical background. So E is Einstein, and P and R are 2 other physicists, and it was one of the arguments they have against quantum mechanics. But they have one argument against quantum mechanics because they think the entangled states are really weird. But people think about it and say, well, this entangling experiment sounds like okay-ish. And so ironically, EPR pair become a name for quantum state. Or even though it was Einstein trying to prove that quantum mechanics doesn't work. But people think about it and do experiment and find out that well, the universe actually works in a way where EPR pair behave as what quantum mechanics would do. Okay, and yeah, so that's EPR pair. So it's EPR, it's the P and R. Okay, and yeah, let's go back to superdense coding. As we said, so the Bell states they will form orthonormal basis, and I guess it's something you can check in your homework. You just check that all of them are normalized and they're orthogonal to each other. Okay. And yeah, so they form orthonormal basis. And what's important is that when we have orthonormal basis, then we say that every orthonormal basis you can do a quantum measurement. Okay, you can have a quantum measurement that just perfectly distinguished states that are in orthonormal basis. Okay. And yeah, then go back to superdense coding protocol. Now the protocol is very simple. So Alice do something on her 1 qubit, and we say the protocol can send 1 qubit from Alice to Bob. And so what Alice will do is just send this 1 qubit, this qubit that's entangled to Bob's qubit to Bob. Okay. And yeah, so. So this is what I do. So Alice just send her qubit to Bob. This is the sending qubit part. Okay. So now Bob has this entangled state totally to his side, and he can do what he wants. And then we say the state is in one of the 4 bases, and so Bob does measure in these 4 bases, naturally. So Bob do a measurement in the 4 bases, and then Bob will know which one of the 4 states it is. Okay, and here we have H1 notation, the build state. Sometimes we also call it beta xy for some xy in 0, 1. Okay. Yeah, so Bob can measure in build basis, and he will know which one of the 4 states is sent, and then he will know which one of the 4 messages that Alice had in her mind. Okay, so that's superdense coding. Superdense coding protocol, and we see that in this protocol, Alice and Bob used one copy of shared entanglement because there was sharing an entangled state between them. But after the protocol, this could become on Bob's side, so they don't share. They don't have this qubit share between them anymore. But as a result, Alice can send 2 classical bits to Bob perfectly. Okay, and yeah, so here are something I want to take about shared entanglement. So the EPR paired are also called maximally entangled state. So here is another name for EPR pair, so maximally entangled state. And so you see this maximal number here means that there is some way to calculate how much entanglement you have on your state. And yeah, there are ways to do this, but I don't think we'll cover in course. This is in the book though, so you can go to later part of chapter. I think probably chapter 7 or 8. There will be teachings about how you calculate entanglement between states. So you can calculate something like entropy. Okay, but anyway, there are actually different ways to calculate entanglement, but all the measures you can use to measure how entangled your state are the EPR pair are maximally value. So it's a maximally entangled state of 2 qubits. Okay. And then the second point about sharing entanglement I want to say is that doesn't contain information. We already say this before, but it's important or it's a good part about the sharing entanglement is that Alice and Bob don't need to know their message, so the shared state size doesn't depend on your 000111011. Okay, so we can imagine maybe Alice wants to send some news to Bob at maybe 7 a.m. each day. And outside of that time, they can just use their downtime to create those shared entanglement. Okay, yeah, and in particular, Alice and Bob can create shared entanglement before Alice even knows the message she wants to send. Okay, so it's nice. Okay, and then we can compare this to other things. Okay, so one thing is so we keep share randomness. So so share entangled state. So this shared entanglement, this 0 plus 1 1 state is kind of like a classical correlated state, right? So you can also say maybe Alice and Bob share. So if you know some cryptography, we know Alice and Bob can share some randomness. Okay, and I guess we talk about shared randomness, right? So in QKD we talk about shared randomness. Alice and Bob might share some random bit string. Okay, and so in particular you can think about is the shared entanglement state. So it's look at this 0 plus 1 1 looks like just something that's either both sides have 0 or both sides have 1 vs share let's see 50%. So so maybe Alice and Bob share one bit of classical randomness. So Alice have a random bit and Bob have a same random bit, and maybe they can get this from QKD. Okay, so say they get this from QKD. And you can think about is this thing just this thing in very complicated form, and then indeed it's different. Okay, so they look a bit similar, but it's very different, and we already proved why they are different. So this shared entanglement is more powerful than shared randomness, because you can show rigorously that if you just have a shared randomness, you cannot do superdense coding. Okay? Yeah, so I guess we can get into this a little more. So you see that in superdense coding, it's important to have this phase here. We kind of encode one bit of the information on the phase between the 0 part, on the phase between this 0 part and the 1 part, or this 10 part and the 01 part. Okay. Yeah, so you see that if you have a quantum state, you can encode the extra bit of information on this phase here. But if Alice and Bob are just sharing classical randomness, then classical randomness don't have any phase. And so they share classical randomness, they still cannot send any form information between them. Okay. Yeah, you can try it more to get a feel about classical randomness. Classical randomness don't help you send information. Okay, and then there is a bad part of shared entanglement is where you want to create them, and assuming Alice and Bob are far away, then you need to use some quantum communication to create them. So you need to use one bit of quantum communication to create one bit of shared entanglement. I guess one pair of shared entanglement, so one EPR pair. And yeah, we see that is a very useful resource. So by using one EPR pair, we can do superdense coding with one bit. Okay, yeah, some resources that get used. Okay, then let's talk about the second protocol. So second protocol today we want to talk about is quantum teleportation. And it's a bit of a weird thing I want to do, but so it's a way to send quantum information by sending classical information. Okay. So yeah, as we say here, quantum teleportation is a protocol that for moving unknown quantum state around, okay, and without having way to send the quantum state. Okay, and but the trick here once again is Alice and Bob will pre-share some entanglement, and so maybe they don't have a quantum channel between them, but maybe they meet sometime. I guess that's kind of like quantum channel, but maybe they meet sometime before, and Bob just take away one qubit from Alice. Okay. And but anyway, they have this pre-shared entanglement. They created it in some way, and now they can only send the classical information between them. So Alice is going to send the classical information to Bob, and the end result is that Bob will have the unknown state from Alice's side. Okay. And I guess here important part is the state is unknown. Okay, so if say Alice knows the state, then she can just send a classical description to Bob, and Bob can create a state. But then from our discussion of unknown quantum state, we know now this is tricky because Alice only get one bit of this unknown state here. So she cannot really know what this state is. This state need to stay unknown, and Bob got it, and Bob will still hold this state as an unknown quantum state. So this state can be really anything. So for example, let's say in our QKD example, this state can be all of 0, 1, plus, minus. Okay? And so if Alice try to learn this state, she learns some basis, she will measure in some basis, and this will collapse the state, and she will never be sure what this state is. Okay? And yeah, so in order to do this teleportation, in order to do this teleportation, they need to somehow make this states as an unknown state, and have Bob got this state as also an unknown state. Okay. So yeah, that's a very interesting part of quantum teleportation. Yeah. Yeah, so that's teleportation. They have generated EPR pair between them, and Alice can only send classical information to Bob, and Alice need to deliver this state to Bob. Okay. And how we do this? Now this is a complicated, more complicated protocol, and but we'll do a lot of things in Bell basis. Okay. Anyway, let's write down what the states Alice and Bob have. And I guess I didn't say, but this unknown state is also 1 qubit. Okay. Yeah, so it's a bit important that so they share a EPR pair, so it's a 2 qubit, and the unknown state to be sent is also 1 qubit. Okay. So anyway, so Alice start with some unknown state, and to be fully general, we say it's some A0 plus B1, okay, with some unknown coefficient A and B. And then we say Alice and Bob also share an EPR pair, and so there is some beta 00 state. Okay, and so the total state of the state of those 3 qubits is this Katassai tensor beta 00. So if you write out everything, it is 1 over square root 2 A0 on 00 plus B1 00 plus 1 1, then plus B1 and the tensor this is 00 also plus 1 1. Okay. And so remember on the start of the protocol, Alice has 2 qubits. So the unknown qubit and 1 part of EPR, and then the third qubit Bob has. So Bob has the second qubit of the EPR. Okay. So this is on Alice. Let's try to mark the Alice part. So Alice part is this qubit, this qubit, this qubit, and this qubit, this qubit, this qubit. Okay, and yeah, let's do calculation. Okay, and so Alice will do things on her 2 qubit, and the first thing she do is she will do CNOT gate. Okay, so we haven't talked about CNOT gate, but CNOT gate is kind of classical gate because it maps computational basis states to computational basis states. And it's well, it's a really classical gate. If you write down in 2x2 matrix, is this because it's a 2 qubit gate, and it's kind of the most important 2 qubit gate for quantum computation, because we can think about quantum computation where the only 2 qubit gate is CNOT. Okay. And but anyway, if you write down matrix, is this, but easier way to see CNOT is that it's a gate where you control on first qubit and decide whether you want to flip the second qubit. Okay, and I guess we have a bit of an example where we have larger. Okay, so say CNOT on 1 1. So if the control qubit is 1, then you flip the target qubit. So it has this notation. So this is control and this is target. And so if the control qubit is 1, then you flip the target qubit. So from 1 to 0. And say if control qubit is 1 and the target qubit is 0, then you flip target qubit from 0 to 1. And then, but if the control qubit is 0, then you do nothing to the target qubit. So this is what CNOT do. Then I guess we have all 4 results of CNOT here. So we have control is 0, then target qubit doesn't get changed. So this is 0 and 1, stay 0 and 1 here. And if control is 1 and the target is 0 and 1, then control is 1, then you flip the target qubit. So this 0 and 1 become 1 and 0. Okay, so this is what CNOT do. It's a get. So you see this is a very classical get. So you just look at the control qubit and flip or not flip the target qubit. And there is a more succinct notation here. So you have 2 A and B as either 0 and 1 here. Then control qubit it will state as what it is. So it is still A here. And then we write B O plus A here. This means XOR. So B XOR A here means that if A is 1, then you will add 1, then you flip here. And if A is 0, then nothing happen here. Okay, so this is CNOT. And yeah, we'll talk a little bit more about it in the circuit part of this course. Okay. And yeah, so first thing Alice do is she do CNOT get, and then the second thing she do is now it's going to be much more complicated. She do headmark get on first qubit. Okay, so first qubit she do headmark get. Okay, first qubit she do headmark get. So the other two qubit doesn't get anything. And let's see what headmark gate do. So headmark gate on 0 will turn into plus state, and headmark gate on 1 will turn into minus state. So you have 0 state become plus state, so basically this thing, and change the normalization a little bit, and then 1 state become this minus state, 0 minus 1. Okay, so headmark 0 is plus, headmark 1 is minus. Headmark 1 is minus. Okay. And yeah, then this is the dirty part of this calculation. We just need to multiply out everything. So now instead of 4 turns, we have 8 turns. Okay. And of those 8 turns, we want to group them together in some nicer way. So we group together what the first 2 qubits are. Okay. So there are some results where first 2 qubits are 0, 0. So from here, say with this turn we have a 0, 0 here. And from here we have a 0, 0 here. Okay, and so this 0, 0 turn, and the third qubit will have this A and a 0 here, and also this is 0, 0 here. We have a B and 1 here. Okay, so this is A0 plus B1. Okay, and yeah, on other turns you have other things. So we have A1 plus B0 and A0 minus B1 and A1 minus B0 here. Okay. So this is write down what the end result. And from here we can kind of see what we want to do. Because you see that if the first 2 qubit is 0, 0, then this A0 plus B1 is exactly the unknown state we want to send. Okay? So we kind of want, well, if Alice happen have 0, 0 on her part, then we are very nice, then we are lucky. Then Bob will already have this A0 plus B1 thing. But if Alice has other things on her part, other state on her part, then Bob has weird state, then what should we do? Okay. And it turns out what we can do is we can correct this thing. Okay. And so this is what we actually do in protocol. So Alice will measure her part. So Alice will try to see whether her part is 0, 0, 0, 1, 1, 0, or 1, 1. Okay. And yeah, so she do orthogonal basis measurement to determine which one of those 4 is on Alice's part. And so each one will, so they are all normalized with this normalization 1 over 2. So each one will happen with probability 1 over 4, so totally equal. And this doesn't depend on our unknown state, so that's nice. And Bob will have the corresponding 4 different states. And so we know already with 1 over 4 probability, our protocol can just end here. So if Alice got 0, 0, and Alice can just tell Bob, say, oh, I got 0, 0, and now you get the unknown state. Okay. And but the next part is, but the hard part is what if Alice get other thing? We want Bob to still get this A0 plus B1. Okay. And so what we do is we correct those states, because we know Alice know the measurement result. Alice know which one of the 4 states Bob got. And Alice can just tell Bob like you got 1 of the 4, and Bob can try to flip all the 3 things back to A0 plus B1. Okay. And so this is what the correction Bob can do. So it's easier to see it here. Okay, so if Bob gets A0 plus B1, then Bob can apply just X here. Okay, then Bob can apply X here, so 1 becomes 0 and 0 becomes 1. Okay, and Bob is A0 minus B1, then Bob can apply a Z gate. So Z gate will get a minus sign on this 1 here, so it's A0 minus B1, go back to A0 plus B1. And finally, if Bob gets this thing, then Bob can do, I think, X first, then Z. Okay. Bob can do X and then Z. Then, yeah, he will flip this back. Okay. And so this is exactly what Bob do. So Alice will tell Bob what's the measurement result, and Bob Bob condition on the measurement result is received will correct his state back to A0 plus B1, and that complete the protocol. And yeah, and then we do a bit of more formulation. So so we can have a bit of I guess more explicit expression here. So we can say Bob receive 2 bits of information here. So Bob will receive result M1 and M2, and then the thing Bob do is he do he do X to the M2 and Z to the M1. Okay. So this is kind of the teleportation protocol in a picture. So Alice will do this. Alice will do this. C0 and headma, and will do 2 measurements, got result M1 and M2, and Bob will see the result M2, and if M2 is 1, he apply an X, and if M1 is 1, he apply a Z, and Bob will get this state. Right, so this is quantum teleportation. So you see that Alice and Bob can pre-share the entanglement, and then they never have quantum communication, because the first 2 qubits is Alice and the third qubit is Bob, and the communication they actually do is I guess is the communication is kind of here, and you see the only thing passed through here are classical lines. Okay, yeah. So in less than 1 minute, let's say a bit about quantum teleportation. Okay. So first interesting point is by our formulation, Bob's state change immediately after Alice measurement. Okay, and so this is what Einstein don't like about quantum mechanics, because why should Alice doing things on her side change Bob's state? But so yeah, so it is exactly here. Alice after Alice doing measurement, Bob's state collapsed to 1/4. Okay. So this is a super key action at distance, and Einstein doesn't really like this, but this is what the quantum mechanics do. But also we say this is kind of okay. So even though we have this spooky action, this spooky action doesn't violate the other thing Einstein like. That is, it doesn't violate relativity. Relativity says that you cannot send the information faster than speed of light. Okay. So this change happens immediately. This is faster than speed of light. So Alice can just do this, and immediately this state change here. But this change of state don't actually tell us any information. Okay. So Bob only learned the information about that until he received the classical information. Okay. So even though this is spooky, it's actually okay because it didn't enable faster than speed of light communication. Okay. And also a bit of counting on information. So as we say, M1 and M2 is totally random, so it doesn't contain information about outside. So it's okay. So our unknown quantum state can stay unknown, and no one can learn anything about it. I guess this is also part of non-cloning. Okay, so if it's unknown, then it must stay unknown, or you measure it in some way and destroy it. Okay, and yeah, and more about non-cloning. So this is a teleportation protocol, not cloning protocol. So at least copy of site will get destroyed. So now at least don't hold a copy of site, but holds a copy of site. And yeah, sorry for going over time. Let's stop here. But I guess one thing I want to say, sorry, 10 minutes, is also you can check yourself that this measurement, so this so why we do this C0 head mark here is because it is actually build basis measurement. Okay, and yeah, so revolve over time, and let's see you on Thursday. And now we'll talk about density matrices.这个是助教的 ，OK。
然后还有一件事情，
怎样？
我之前中央学长就要我一起打一个 AI 的比赛，然后那个 AI 比赛要填指导教授，然后